Scientists have calculated that if a Carrington-level solar storm were detected today, we would have approximately 30 minutes of warning. 30 minutes to ground every plane. 30 minutes to protect every satellite. 30 minutes to decide whether modern civilization survives. We have never successfully completed that procedure. Not once. There is a particular kind of danger that does not announce itself with sirens. It does not build slowly enough for governments to respond, or fast enough to appear on the news before it arrives. It exists in the space between detection and impact, between knowing and doing, between a warning and a consequence. The Carrington Event of 1859 was that kind of danger, and it is coming back. The question is not whether we are prepared. The question is whether preparation is even possible for a civilization that has spent 2 centuries building systems that are, by their very nature, vulnerable to the one threat we have always known was coming. To understand what is approaching, you have to first understand what has already happened. On the morning of September 1st, 1859, a British astronomer named Richard Carrington was doing what he did every clear morning. He was observing the sun. He had built a small observatory at his estate in Surrey, and through his telescope, he was tracing the outlines of a sunspot cluster, a dark, magnetically turbulent region on the solar surface, roughly 10 times the diameter of Earth. At approximately 11:18 in the morning, something changed. A burst of white light, intensely bright, erupted from the edge of the sunspot. Carrington watched it for perhaps 5 minutes before it faded. He immediately wrote down the time, sketched a position, and rode to the Royal Astronomical Society in London to report what he had seen. He suspected it was significant. He had no idea what he had witnessed. What Carrington observed was a solar flare, a sudden violent release of magnetic energy from the sun's surface. But the flare was only the beginning. Accompanying it, and partially caused by it, was something far larger, a coronal mass ejection. A billion-ton cloud of magnetized plasma hurled outward from the sun at several million kilometers per hour. It was aimed directly at Earth. Under normal circumstances, a coronal mass ejection takes 2 to 4 days to cross the distance between the sun and our planet. This one arrived in 17 hours. The plasma was moving so fast that it had compressed the journey by more than half. That single fact should tell you something about the scale of what was coming. When it arrived, it hit Earth's magnetic field like a fist into a membrane. The field stretched, distorted, and partially collapsed. What followed was the most powerful geomagnetic storm in recorded human history. The effects in 1859 were, by the standards of that era, spectacular rather than catastrophic. Aurora Borealis, the northern lights, appeared not just over Scandinavia and Canada, but over Cuba, the Bahamas, Colombia, and as far south as Hawaii. In the southern hemisphere, aurora australis were visible north of Brisbane. People who had never seen the northern lights in their lives stepped outside at midnight and found their streets bathed in red, green, and purple light. Some thought the cities were on fire. Some thought the world was ending. A few simply stood and stared at something they would spend the rest of their lives trying to describe. The only technology seriously disrupted was the telegraph network. Telegraph operators across Europe and North America reported their equipment sparking, smoking, and in some cases bursting into open flame. The induced current was so powerful that operators who disconnected their machines from their power supplies found the equipment continued to function, driven entirely by the electromagnetic energy pouring through the atmosphere. Some operators reported being able to send and receive messages for hours on solar power alone, entirely unintentionally. It was, depending on your perspective, either a curiosity or a catastrophe narrowly avoided. At the time, most observers chose the former interpretation. The world had survived. The skies had been beautiful. The telegraph lines could be repaired. And the scientific community filed the Carrington Event away as an extraordinary anomaly, a once-in-history phenomenon that was unlikely to repeat. That interpretation was wrong. Here is what we now know about the Carrington Event that was not understood in 1859. It was not unique. Ice core samples taken from Greenland and Antarctica preserve a chemical record of solar activity going back thousands of years. Spikes in certain isotopes, beryllium-10, chlorine-36, appear in the ice at regular intervals, each one corresponding to a massive injection of cosmic radiation. From the Sun, the record shows events comparable to or exceeding the Carrington storm occurring roughly once every century on average, over the past several thousand years. In 774 AD, an event now called the Miyake Event deposited the largest carbon-14 spike ever recorded in tree rings across the world. The energy released was several times greater than the Carrington storm. We do not know exactly what caused it. The leading hypothesis is a solar superflare of a magnitude we have never directly observed in the modern era. A smaller but still significant event occurred in 993 AD, and its signature is preserved in timber from Viking Age settlements that archaeologists still use today to date Norse artifacts. The 1859 event was not a once-in-history anomaly. It was a recurring phenomenon. The Sun does this. The Sun has always done this. And the interval between extreme events is measured not in millennia, but in decades. In fact, we came close to experiencing another one within living memory. In July 2012, a coronal mass ejection of extraordinary magnitude erupted from the Sun's surface. It was, by the measurements of NASA's Stereo spacecraft, comparable in intensity to the Carrington Event of 1859. Some estimates suggest it may have been stronger. The plasma cloud traveled through space at a speed that, had it intersected with Earth's orbit, would have given us fewer warning hours than the original Carrington impact. It missed Earth by 9 days. 9 days earlier in its orbital position, and Earth would have been directly in the path of that ejection. 9 days. The planet rotates around the Sun at roughly 2.6 million kilometers per day. The margin between the 2012 event and a direct hit was, in cosmic terms, essentially nothing. Daniel Baker, a physicist at the University of Colorado who led the analysis of the event, stated that had the ejection hit Earth, it would have been a decade-long catastrophe. Not a storm, not a crisis. A decade-long restructuring of what modern civilization looks like. The storm came and went. Most people on Earth never heard about it. The news cycle was occupied with other things, and the near miss was filed, again, under the category of interesting scientific data rather than existential warning. To understand why 2012 was different from 1859 in every way that matters, you have to understand what changed between those two moments. And what changed is not simply technology. What changed is the nature of civilizational dependency. In 1859, the telegraph was the most electrically sensitive infrastructure on the planet. It was a network of copper wire strung between wooden poles across continents. Damaging it was inconvenient, expensive, disrupting in the way that a bad storm is disrupting. But the telegraph was not load-bearing infrastructure. The world did not depend on it for food, water, heat, medical care, or military coordination. If it went down, people wrote letters. Today, the situation is categorically different. There are currently more than 19,000 satellites in orbit around Earth. They provide GPS, navigation for every commercial aircraft, every shipping container, every military drone, every smartphone. They relay financial transactions across continents in milliseconds. They monitor weather systems, coordinate emergency services, guide agricultural machinery across fields, and provide the timing signals that keep global data networks synchronized. Remove them, not destroy them, simply disable them, and the systems they support begin to fail within hours. On the ground, the situation is equally fragile. The global electrical grid is composed of hundreds of interconnected regional networks, each one dependent on large, custom-manufactured transformers that step voltage up and down across transmission lines. These transformers are not mass-produced. They are built to order. The lead time for a single large transformer is typically between 12 months and 3 years. The United States alone has several thousand of them in active service. The global manufacturing capacity to replace them does not exist on any timeline that a civilization without power could wait for. A Carrington-level geomagnetic storm induces current in long conductors. Power lines are long conductors. The longer the line, the greater the induced current. The greater the current, the more likely the transformer at the end of that line overheats and fails. Not trips a breaker. Not shuts down temporarily. Fails permanently in a way that requires physical replacement of a component that takes years to manufacture. This is the mechanism by which a solar storm becomes not a blackout but a restructuring. The cascades that follow a grid failure of sufficient scale are not linear. They do not proceed in an orderly sequence that emergency managers can work through one step at a time. They compound. They interact. They produce effects that no single agency is positioned to manage because no single agency was designed with this failure mode in mind. Consider water. Municipal water systems require electricity to operate. Pumping stations that move water from reservoirs through treatment facilities and into distribution networks. Without power, water stops moving within hours. Without water, hospitals cannot operate. Fires cannot be suppressed. Sanitation fails. And the human body, in most climates, begins to experience serious physiological stress within 3 days of adequate water deprivation. Consider food. The modern global food supply chain operates on just-in-time delivery principles. Warehouses carry days of inventory, not weeks. Grocery stores typically hold 72 hours of supply for their local population. Refrigeration fails when power fails. The cold chain, the unbroken sequence of refrigerated transport that keeps perishable food viable from farm to consumer, dissolves almost immediately in a sustained grid outage. What remains is shelf-stable food, unevenly distributed, with no functional logistics network to redistribute it. Consider communications. The internet is not a wireless network. It is a physical infrastructure of fiber optic cables, data centers, routing hardware, and undersea cables that span every ocean. Data centers require continuous power and continuous cooling. Without both, they shut down within hours. The undersea cables that carry the majority of international data traffic are, themselves, powered by electricity transmitted through the cable, electricity that comes from the grid on either end. When the grid fails, international communications fail with it. Consider finance. Every financial transaction that occurs in the modern world, every payroll deposit, every supply chain payment, every government transfer requires network connectivity, functioning servers, and synchronized timing signals from GPS satellites. In a sustained infrastructure failure, the financial system does not slow down. It stops. And without the financial system, the organizational capacity to coordinate recovery, to pay workers, to procure equipment, to move resources, collapses alongside everything else. These are not independent failures. Each one accelerates the others. And the compounding of these failures is not something that emergency planning has ever fully modeled, because the scale of the scenario falls outside the parameters that planning exercises are designed to address. There is a concept in systems theory called a single point of failure. It refers to a component whose failure causes the entire system to collapse, a component with no redundancy, no backup, no graceful degradation pathway. The more complex a system becomes, the harder it is to identify these points before they fail, because their criticality is often invisible during normal operation. The Carrington scenario exposes multiple simultaneous single points of failure across every major infrastructure system on the planet simultaneously, faster than any of those systems can adapt. This is the architecture of modern civilization. Not fragile in any individual component, fragile in its interconnection, fragile in the assumption, built into every layer of the system, that the electromagnetic environment will remain stable, that the grid will stay up, that the satellites will keep transmitting, that the timing signals will continue. Those assumptions have been valid for long enough that most institutions no longer treat them as assumptions. They treat them as facts. So what, precisely, is the warning system we rely on? There are currently two primary assets in the solar monitoring network. The first is NASA's Advanced Composition Explorer, known as ACE, positioned approximately 1.5 million kilometers from Earth at the Lagrange point between our planet and the Sun, a gravitational equilibrium, where a spacecraft can maintain a stable position without continuous propulsion. From this position, ACE monitors the solar wind and can detect the magnetic field orientation of an incoming coronal mass ejection. That orientation is the critical variable. A coronal mass ejection carries its own magnetic field. If that field is oriented in the same direction as Earth's, what physicists call a northward orientation, the two fields repel each other and the plasma deflects. The storm passes. The aurora is spectacular. The grid survives. But if the incoming field is oriented southward, opposite to Earth's, the two fields couple. They merge. And when they merge, the plasma pours directly into Earth's magnetosphere, inducing the geomagnetic currents that destroy transformers and overwhelm satellites. ACE can detect this orientation. But ACE sits only 1.5 million kilometers from Earth, and a fast-moving coronal mass ejection crosses that distance in approximately 20 to 30 minutes. This is the 30-minute window. From the moment ACE detects a southward-oriented, high-velocity coronal mass ejection to the moment it hits Earth's atmosphere, 30 minutes. In that window, every aircraft currently in the air must be instructed to land. Every satellite operator must put their systems into safe mode, powering down sensitive electronics and orienting solar panels away from the incoming plasma. Grid operators must perform controlled shutdowns of major transmission lines to prevent the transformer failures that would otherwise cascade through the network. This is not a theoretical protocol. It exists. The procedures have been written. The communication channels have been identified. The agencies responsible for each component of the response have been designated, but the procedure has never been executed under real conditions, never fully tested, never completed against a real timeline with real stakes and real organizational friction. And the assets we depend on to execute it are themselves aging. ACE was launched in 1997. It was designed for a 5-year mission. It has been operating for more than 2 decades past its design lifespan, maintained through a combination of engineering ingenuity and institutional inertia. Its replacement, the Deep Space Climate Observatory, DSCOVR, was launched in 2015, but has experienced its own technical difficulties. The solar monitoring network is not robust. It is a thin line of aging hardware between an indifferent star and a civilization that has forgotten what darkness looks like. There are people who study this problem with genuine rigor. Physicists, grid engineers, emergency managers, intelligence analysts. They have written reports, conducted exercises, testified before legislative committees. The technical literature on the geomagnetic storm threat is not sparse. It is detailed, specific, and, in many places, alarming. A 2013 report from Lloyd S. of London, an institution not given to sensationalism, estimated that a Carrington-level event hitting the United States alone could cause between $0.6 and $2.6 trillion in damage and leave between 20 and 40 million people without power for periods, ranging from 16 days to 2 years depending on which transformers failed. The variance in that estimate is not uncertainty about the physics. It is uncertainty about which transformers would fail first, how the cascade would propagate, and how quickly the international manufacturing and logistics system could respond, a system that would itself be impaired by the same event. A 2008 report from the National Academy of Sciences described the societal implications in terms that rarely appear in scientific literature. It used the word catastrophic without qualification. It outlined, in systematic detail, the failure of water, food, transportation, communications, and financial systems. It estimated recovery timelines not in weeks but in years, contingent on factors, international manufacturing cooperation, functional governance, maintained social order, that themselves become uncertain when infrastructure fails at scale. These reports were read. They were filed. Some policy changes occurred. Not enough. Not fast enough. And the political attention required to harden the grid, to stockpile spare transformers, to upgrade monitoring satellites, to conduct and complete the 30-minute protocol under PVFOCA under Ken. Genuine exercise conditions has never materialized at the scale the problem requires, because the problem has no constituency. It produces no immediate harm. It competes for attention with every other crisis that is happening right now, visibly, with consequences that are already being felt. The solar threat is the kind of danger that only becomes politically legible in the moment it arrives. And in the moment it arrives, 30 minutes is not enough time to build the political will that should have been built over decades. There is a pattern here that extends beyond the Carrington scenario specifically. Every civilization in history that has collapsed not because a threat was unknown, but because the response was insufficient relative to the scale of the threat. The Romans understood that the empire's borders were overextended. The administrators of the Bronze Age Mediterranean knew their trade networks were fragile. The Minoan civilization on Crete watched the volcanic island of Thera smoke and rumble for weeks before the eruption that ended their world. In each case, the information existed. The capacity to respond existed. The response did not occur at the necessary scale. This is not a story about incompetence. It is a story about the structural limits of how civilizations process existential risk. The threats that kill civilizations are rarely the ones that feel urgent in the moment. They are the ones that feel manageable until they are not. The ones that are always deferred to the next administration, the next budget cycle, the next report that will finally make the case clearly enough for action. The Carrington scenario is, in this sense, not simply a technological problem. It is a civilizational stress test. It asks whether a species capable of building a global electrical grid is also capable of protecting one. Whether the same intelligence that enabled us to become dependent on electromagnetic infrastructure can also sustain the political and institutional will to make that infrastructure survivable. That is, in the most precise sense of the term, a great filter question. The Fermi paradox asks why, in a universe of hundreds of billions of stars, many of them older than our Sun, and many of them hosting planets, that should by the laws of physics and chemistry be capable of supporting life, we have found no evidence of any civilization other than our own. One answer is that civilizations do not survive long enough to become detectable. They emerge. They develop technology. They become dependent on that technology. And at some point, at some specific moment in their development, they encounter a challenge that their technology creates their vulnerability for, but their institutions fail to address, and they fail it. The filter in this interpretation is not an asteroid. It is not a pandemic. It is not a supervolcano. It is the gap between what a civilization knows and what a civilization does with what it knows. It is the distance between a warning and a response, between a 30-minute window and the procedure that fills it. Every civilization that reaches our level of technological development necessarily reaches a point where its infrastructure becomes both powerful enough to sustain billions of lives and vulnerable enough to be disrupted by phenomena that predate the civilization by billions of years. The Sun was producing coronal mass ejections long before the first multicellular organism evolved on Earth. It will produce them long after whatever comes after us. The only question that matters, is whether the window between knowing that and doing something about it is longer than 30 minutes. In 2012, 9 days separated us from that test. In some year between now and 2035, solar physicists give it a probability of roughly 4% per year during active solar periods, which compound, we may not have 9 days of margin. We may have 30 minutes. And in those 30 minutes, every assumption our civilization is built on, that the lights stay on, that the water flows, that the planes land safely, that the data centers keep running, that the financial system processes the transaction, will be tested against the physics of a star that does not negotiate. We have built the most complex, interconnected, and productive civilization in the history of this planet. We have done it in 200 years. We have built it on electricity, on electromagnetic signals, on systems of such breathtaking interdependence that the failure of any single layer sends tremors through every other. We have never seriously asked what happens when the star that powers all of it decides to remind us of the terms. Somewhere above you, right now, in the outer atmosphere of a star 150 million kilometers away, magnetic fields are twisting. Energy is accumulating. Plasma is building against boundaries that have held for weeks or days or hours. The Carrington Event is not history, it is a frequency. And we are long overdue for the next transmission. The question is not whether we will receive it. The question is whether 30 minutes is enough time for a civilization to remember what it built, understand what it risked, and decide whether it deserved to survive.